Welcome to Easy Math TV. We're going to continue our series on statistics and talking about different kinds of random variables and different kinds of distributions. And now we're going to enter into a totally new kind of random variable as well. And it's a continuous random variable. So we're going to start with the simplest kind of distribution that we have of a continuous random variable, and that is a uniform distribution, continuous uniform distribution. So you've already seen a discrete uniform distribution, and you're going to have to put aside some of the things that you learned from that, because there are some very essential differences between a discrete random variable and a uniform random variable that are going to change how we approach this type of a problem. So let's start with a couple of really important facts. For any continuous distribution on a closed interval a comma b, so basically that's just a generic term for a closed interval with a left endpoint of a and a right endpoint of b. So it can be any closed interval at all. But to make things simpler, we're going to just use a specific one. We're going to use the closed interval from 0 to 5. So x equals 0 is the smallest value that we can have, and x equals 5.00 is the largest value. And then x can take on any decimal value in between that. So, think in terms of like, I don't know, the amount of rain that we're going to get in the next storm that's coming our way is going to be somewhere between 0 and 5 inches. I mean, 5 inches is kind of terrifying, but it is what it is. So think of that as an example where we are measuring something that is on a continuous scale. It is considered to be continuous because there are an infinite number of decimal places that we could go out to for any of the measurements that happens within that range that we have. Okay, so measurements, lengths in inches, lengths in centimeters, that's all continuous. Temperature is continuous. There's a lot of different things. Weight is continuous. Lots of different things that we measure out there that are on a continuous scale. So we just need to remember that this is a pretty common thing. And when you calculate the mean, for example, the mean of any distribution, even if it's a discrete distribution, when you calculate the mean is on a continuous scale. The standard deviation is on a continuous scale. So those really important statistical measures are all continuous random variables. We already know what a discrete random variable is. So just to compare those two things, discrete outcomes are individualized. Like, we can talk about each individual outcome, and if we want to allow more than one possible outcome, we calculate their probabilities simply by adding them up, right? We add up the different probabilities of all the outcomes that we want to include. The equivalent of that on a continuous scale is to calculate the area. So that's not something that you're entirely familiar with if you've never had calculus before, because it's in calculus that we start introducing this idea of area under a curve or under a graph. So we don't need calculus, though, for this, because we're talking about just areas that are going to be rectangles. So we're going to get into that in a moment. All right, consider our population, which is the interval from 0 to 5, and pick any number in that interval, okay? So any number at all. So let's just pick at random. We're just going to pick one. Let's just say it's x equals 2, all right? The thing we need to wrap our head around right now, right off the bat, is that it is a fact that the probability of x equaling a specific number, one number, is always going to be 0. So probability of x equals 2 is equal to 0. Probability of x equals 3 is equal to 0. Probability of x equals 1/2 is equal to 0. You just pick any number at all and replace the 2 with it, and the probability that x is exactly that is always going to be 0 when we are on a continuous random variable. So let me unpack a little bit as to why that is. So why is that true? Well, so I've already said this, there are an infinite number of choices just on the interval between 2 and 3 alone. So to visualize that, though, let's pretend that we can only measure out to 3 decimal places. Then we could actually list the numbers. We would have 2.000, comma, 2.001, comma, 2.002. You see how that's going? And then the next one would be 2.003. And you would just keep increasing that decimal portion by 1 each time up to 2.999. And then the next number would be 3.000. So if you could list all of those out, which we could, but it would take a long time, there would be 1,000 numbers on the list. So now go out to 4 decimal places, and we would have 10,000 numbers on the list. If you go out to 5 decimal places, you would have 100,000 numbers on the list. And that's just in the interval between 2 and 3. Now we want to include the interval from 0 to 5. So we've even expanded it more than that. So the probability of choosing just one number out of those 10,000 or 100,000 is too small to measure. Too small to measure. And that's why we say that the probability of a single number is going to be 0. It also has to do with the fact that if probabilities are areas, and we're talking about a single number that has no width, what's the area of a rectangle that has no width? It's 0. Okay? The area of a rectangle above a point is just a line, and it has no thickness. It has no density. So therefore, its area is equal to 0. Okay? So that's the other reason. All right, so we need to just get that into our heads right away. If I'm dealing with a continuous random variable, the probability of a single outcome is just 0. All right. So in front of us, we see a graph of what the uniform distribution looks like on the interval 0 to 5. So the first thing that I might be curious about is why does the height of it, why does the top of it end at 0.2? If you notice that 0.2 is the number on the vertical axis over there, that gives us the height of all of our rectangles if we were to make different rectangles and a histogram and whatnot. The heights of all of those things are at 0.2. So why is that? Well, if we take the length of the base, which is the total interval from 0 to 5, has a length of 5. Multiply that by 0.2. That's your total area. So the total area of any continuous probability distribution, the total area has to equal 1. Okay? Always has to equal 1. So we had to choose a height here. We had to choose a height that gave us a total area between the blue rectangle you see here and the orange rectangle. Both of those, when you add those up, you have to get 1. So that's how you construct it. Now let's talk about some probabilities of specific outcomes. So let's talk about the probability of x being less than 2.5. And what I've done here is I've drawn a rectangle that covers the values from 0 to 2.5, because that's what x less than 2.5 is. It's 0 to 2.5. And drawn the rectangle up to the line, which is at 0.2. So the total probability of that is going to be the area. Area is base times height, right? So base times height is 2.5, that's the width, times 0.2, which is the height. So get this out again. 2.5 times 0.2 equals, it's exactly 1/2, 0.5. So 0.5 or 1/2, which makes sense because what we've done is we have split up our 0 to 5 interval has been split into two equal pieces, right? 0 to 2.5 is exactly halfway. So because it's a uniform distribution, we expect the area of the first half to be the same as the area of the second half. We expect those two areas to be exactly the same. All right? So the answer to that question, probability of x less than 2.5 is 1/2 or 0.5. Now let's look at the probability that x is greater than 3. The probability that x is greater than 3 is going to be shown by, we're going to just stretch, we'll move the orange rectangle so that it only covers that portion. So you'll notice that the values of x that my rectangle covers is from x equals 3 to x equals 5, because that's greater than 3. It has to stop at 5 because it doesn't go past that point, and it has to start at 3, right? So the orange rectangle here is showing you the area or the probability that x is greater than 3. It's showing it to you on the graph. That's how you would visualize it on this graph. So now, again, take the base, the length of the base, and multiply by the height. So the base is 2, right? And because going from 3 to 5, think about the width of that. From 3 to 5, 5 minus 3 is 2. So the length of that is 2, and the height is always going to be 0.2 in this. Sorry, I made a 9.2. 0.2. Because we're dealing with a uniform distribution on the interval 0 to 5. So that is not going to change. The 0.2 is not going to change unless we changed our population. If we expanded our values of x, then we would have a different height here. So 2 times 0.2, let's do that. 2 times 0.2 equals, that's 0.4. Which is basically 4/10 or 2/5. So the probability that x is greater than 3 on a continuous uniform distribution on the interval 0, 5, right? So we're starting there, and the probability that x is greater than 3 then is equal to 4/10 or 0.4. So that's 4/10 of the total area. That's our 4/10, the orange that you see there. So in the next video, I'm going to show you how to actually create a grouped frequency data table for this particular distribution, and that might help to clear up some of the confusion about like the differences between a continuous random variable and a discrete random variable. But hopefully this helps you to understand some basics of what the continuous uniform distribution is all about. Like, subscribe, comment down below, share these videos with people if you think they might find them helpful, and I'll see you in the next video.